Everybody, can you hear me? Okay. All right. Okay. Like we're getting a crowd now. Before I pick up where we left off last time, are there any questions? Okay. Start sharing my screen regardless, I guess. Okay. So yeah, just a reminder, I have my office hours at starting at 4 immediately after lecture, or about five minutes after lecture. And Rose, our TA, had her first office hours last night, and I think, and the undergraduate TA, Kevin, is having his first office hours tonight at 8 p.m. And there's Zoom links for these on Canvas. Okay, so let's pick up where we left off last time. So last time we introduced the notion of a good kernel. So a good kernel or an approximate identity. So good kernels or approximate identities. Was a family of functions Kn on T such that I think property A 1 over 2 pi minus pi to pi so these integrate to 1. They have total total integral 1. If we put absolute values inside the integral, they're bounded, so there exists an m bigger than 0 such that these are this is for every n. So there's an m that's independent of n, for which these are bounded in absolute. The family is bounded in an absolute value. Their integral is bounded. And property C, if I look away from 0, then as n goes to infinity, integral of the absolute value of the kernel vanishes. So there's for every delta bigger than 0, the integral over delta less than or equal to absolute x less than or equal to pi of k and x dx goes to 0 as n goes to infinity. So I'm using two different both uppercase and lowercase n's by accident here. Let me fix that. Let me just quit. Okay, so this is a good family of kernels. This is a definition, what it means for a good to be a good family of kernels. And the theorem that will attach to them, the reason why a family of kernels is the following: is that if and let's say n equals 1 to infinity is an approximate identity. Then Kn convolve with F converges to F uniformly on T for all F that are continuous on T. So if you have a good family of kernels, or if you have an approximate identity, if you take a continuous function, convolve with the kernel, and then take a limit as n goes to infinity, you recover the function back again in the sense of uniform convergence. So this is why these are called approximate identities, right? It's approximately an identity under convolution, approximately the convolution identity, right? In the sense of viewing this convolution as an algebraic operation. So in the book, there's a weaker version of this statement where, okay, it's you could take Riemann integrable F, and then you have convergence at points of continuity, at any point of continuity for F. We'll just prove this slightly less weak version, and you can look in the book for the for slightly more general version of this theorem. So what's the proof? Well, we'll use all three properties, of course. So one, the first property is that we have unit mass for Kn. So if I take so I'm going to consider the difference F convolve with Kn minus F, and let's consider this at a point X. This in absolute value is equal to, well, maybe I'll write it like this. So remember what the convolution is. It's 1 over 2 pi integral from minus pi to pi of f of x minus y k n of y dy. And then I'm going to rewrite f of x as f of x times the integral of kn of x, of kn. Right, I'm free to do that. So this is equal to, because that it integrates to 1, I'm just going to multiply by 1. So this is minus 1 over 2 pi integral from minus pi to pi kn of y dy, which is equal to 1 times f of x, an absolute value. And then I'm just going to write this as one integral. So this is by A, by property A of Kn being a good kernel. So this is equal to absolute value of 1 over 2 pi integral from minus pi to pi of f of x minus y minus f of x times kn of y dy. Okay, and all right, so now I've made my definition of KNs, and I presumably want to use some of the other properties. I've exhausted property A already. So now to conclude, I need to use something else that I'm assuming, of course, right? So one thing I'm assuming is that F is continuous, right? And that means, and here, that looks useful in estimating this difference, right? Using the continuity of F, but only if Y is very close to X, right? Only if, only if Y is very close to X or X is close to Y. And what do I have freedom for in this? Maybe I've written this poorly in my notebook. But so if I take, if I look at all small y's, if I look at y very small, then these two are close, right? I'm adding a small number. I'm adding a small number to x here. So I'm going to split the number. I'm going to pick. Um, um, so this is. I'll specify delta at the end, I guess maybe. This is equal to or less than or equal to the integral. So 1 over 2 pi. I'm going to put absolute values inside, but only after I split the integral in two pieces. So all y less than delta of x minus y dy plus 1 over 2 pi all y is bigger than delta between delta and pi of okay. And so like I was saying, this first line I can make small by using the continuity of f. And then the second line, I can use property C for the kernels, right? Since f is a continuous function, okay, I might have twice the maximum of this might contribute twice the maximum that f takes, right? But then I'm integrating away from 0, so I know that as I let n go to infinity, this integral is going to tend to 0. And up top here, I can make this as small as I like, right? So now what are we trying to do? We're trying to show that that for any epsilon, there exists a capital N such that this quantity is smaller than epsilon for all n bigger than or equal to capital N, right? And then for uniform convergence, I want to be able to choose epsilon independently of x. Well, how do I do that? Well, so fix epsilon. So fix epsilon. Find, let delta above be such that f of x minus y minus f of x is less than delta for every is less than, sorry, let's say less than epsilon for every y less than delta. And I can do this so since this is a compact interval, f is continuous and hence uniformly continuous on t. So I can choose this delta independently of x. And then so if I continue this chain of inequalities, the first line is less than or equal to some constant times epsilon times the maximum that the integrals of the kn's take times m, where m is as in the definition of a family of good kernels. And then the second line, so let me make one more comment up here, and let b bigger than 0 be such that f of x is less than or equal to b for every x in t. The second line, I might get some constant times 2 times b, right, the maximum that f takes, times integral delta less than y less than pi of k and y dy. And so this last integral, this thing tends to 0 as n goes to infinity. And here I have this first, I can just take epsilon, this one I can, right, I've made it as small as I like. This first thing, epsilon is arbitrary.
Professor, could you elaborate, what is m in the first?
Sorry, yeah, so m, I'm gonna scroll back up just for a second. M is from part B in this definition of what it means for f to be an approximate, k to be an approximate identity. So what I did here is I just pulled out epsilon from this difference, and then I bounded the rest by b. So this is, so if I just highlight this. This for this I used by property B, and this last one is by C, and the definition of a good family of kernels. Any questions about this?
Yeah, where are these like C's coming from?
So C is like, I guess C here is 1/2 pi.
Oh, you just, instead of writing the constant.
Instead of just, yeah. So I'll do that a lot in this class. So if there's a constant that doesn't matter much, I'll just start writing a letter C. Then later in the class, as we get more comfortable, I'll stop doing that and just and I'll stop doing that altogether and just so another way of writing this is less than or equal to with a little twiddle below. Just save even more notation. I can totally write epsilon times m plus or just epsilon, because m was another constant, didn't matter what it was. Epsilon plus where this notation means less than or equal to C times the quantity that's that I wrote. So when in a lot of these arguments that we're going to make, so a big difference, and I tried to make one of the homework problems reflect this a little bit. A big difference in this class, as opposed to say what you do in 100B, is that a lot of the estimates that we're going to make are quantitative estimates. There's no this one's not a quantitative estimate, but where we're going to want to know rates of decay and things like that. And so oftentimes what we'll, in order to like hone in on that type of conclusion, we'll often try to just, we'll just ignore unimportant constants in the proof, which are something that's just, a number that you could tell me if needed, right? We're given a function f, we could find its maximum if we need to, but it's really not important for the conclusion we want to draw, things like that. So yeah, these C's are just, I think up here, they're just 1/2 pi's that I just dropped.
Okay, cool.
Thanks, guys. Let me rehash that or reload this. Okay, so this is wonderful. We've now proved a general theorem that says that if we have a good family of kernels, then if I convolve with the kernel, with a good family of kernels or with an approximate identity, and let my parameter tend to infinity, then I recover the function again. I get uniform convergence to the function. And the application that we had in mind was recall that the partial Fourier sums of a function can be written as f convolved with dn of x, where dn's are the Dirichlet kernel. Are called the Dirichlet kernel. Dn of x is equal to the sum from minus n to n of e to the I in x.
Quick question.
Yeah.
I just missed the last couple steps of that proof. So we had like the upper bound, but like we take a couple of limits. I just missed like the order.
The order of limits and stuff, and making
yeah.
Things. Okay, so first at the outset, let's pick an epsilon, and we're going to try and show that this is less than epsilon by taking n large enough, right? Independently of it. So I'm going to try and find an epsilon that's independent of x, for which this quantity is small for large enough n. Here, stay on the, who am I talking to? Sorry, who is speaking?
It's me.
Michael.
Yeah.
Michael. Okay. So let me know if you're with me. So that's the goal. So pick this epsilon, right? And now our goal is to choose n large, right, at the end. So once we've picked this epsilon, I wrote it all the way down here instead of at the top. And then now find it, now I'm going to decide how to split up these two integrals by choosing a delta. And the way I'm going to choose delta is I'm going to choose it so that this quantity is less than epsilon as long as y is smaller than delta. So I'm going to use the uniform continuity of f to now fix a delta. All right. And so once I've done that, then I obtain this this inequality, which is I think admittedly sloppily written, but is this okay? Where I use part B on the top line and part C of being a good kernel on the bottom line. Or I haven't used C yet, actually. I've just done this bound like this. And now now the last step, the last thing I'm going to do is I'm going to take n large. This first one had nothing to do with n, right? It did have something to do with n. It was a statement that that the integral of the absolute value of kn is uniformly bounded in n. So it doesn't matter what n is for me to get this. N is gone in this to obtain this part of the conclusion. And now I let n be large. And by letting n large here, I can make this be as small as I like. In particular, I can make it smaller than this thing, smaller than epsilon. And then at the very end, I get something that's less than or equal to some constant times epsilon.
Yeah. Okay.
And then I could have been like, I wanted to see epsilon without a constant in front of it. I could have been more careful about how I chose delta, for example. Right.
I was just getting hung up on, we got like 7 epsilon or something, like if it doesn't matter.
Yeah. We at the end we get like 7 epsilon or something, so it's okay.
Okay, thanks.
Great. Yeah, that all that stuff is super important. Is like how we let things be small. People make mistakes about this all the time for the rest of their lives. I make mistakes like that all the time. Okay, so now let's go back to the problem that we're interested in, namely convergence of Fourier series. And I've just spent a whole bunch of time talking about approximate identities, these good kernels, and have the Fourier series, the partial Fourier sums being represented as f convolved with a family of kernels. So let's check. So we'd be done, and we'd answer Fourier's question if we can show that the dn's are an approximate identity or a family of good kernels. So is this family an approximate identity? So that's our question. We can check property. Let's check. And for those of you who have started the homework or will come to office hours and see Samuel's presentation, part 1 is, it looks good. So 1 over 2 pi minus pi to pi dn of x dx is equal to 1, right? Because if the only thing that contributes is when n equals 0 to the integral. We did this computation earlier in the class. If I integrate over this whole interval length 2 pi, then e to the I n x integrates to 0 as long as n is not 0. So the only thing that contributes to this integral is when little n is equal to 0. So this is equal to 1. That looks good. But b is going to b fails. And there's one of the homework problems is to show this. But let me record some estimates. And this is the estimates you're gonna prove in your homework. So on the one hand, we can write a nice formula for dn of x. So this is a nice formula, but then this is a nice formula, but we can also express this in terms of sines, the sine function. So this is equal to sine of a little bit of a funny factor here, n plus 1/2 x divided by sine of x over 2. And then you can show, well, what's this look like? The picture for the Dirichlet kernel is that it's oscillating away from 0. Let's, if n is pretty big, then it has a bump at 0 and then oscillates some more. And if I think about letting x go to 0, remember sine of x looks like the function x, or sine of y looks like y. So near 0, this function just looks like n. And in fact, I can bound it by up top. I think this is bigger than this function sits below n. And away from 0, if I'm away from 0, I can do something kind of brutal and just say, well, this numerator is less than or equal to 1, right, in absolute value, and the denominator is like x, right? So away from 0, I get this. I can use the function 1 over x. This is the function 1 over absolute x. So I obtain the bound in absolute value. This is less than or equal to the minimum of n and 1 over x. Whichever of those two numbers is smaller, I'll use that one. I don't want to use 1 over x near 0 because 1 over x blows up near 0. But near 0, at 0, the best I can do is capital N, because this function looks like capital N near 0. So that's an upper bound, which isn't too much, isn't too useful if I'm going to try to show you that this fails to be a good kernel. But it's also not good enough to show. Okay, so clearly this bound is not good enough to show that this is a good kernel because, like 1 over x is a badly behaved integral, and then at 0 I just get capital N. But in fact, you can show that there exists a c bigger than 0 such that 1 over c times log n is less than or equal to integral 1 over 2 pi absolute dnx dx, which is less than or equal to c times log n. So you can estimate how big this integral is. It's comparable to log n, which tends to infinity. The lower bound, in fact, tends to infinity as n goes to infinity, right? So this fails to be a good kernel. So property B fails. Dn is not a good kernel, or the family is not a good family of kernels. It's not an approximate identity. All right, so let's give up. We developed some nice theory, and but for the Fourier series, the convolution with a family of kernels, but they fail to be good kernels, and I can't deduce uniform convergence for continuous functions. Okay, well, obviously we're not going to give up, but that's not great. You might be asking why we spend so much time talking about good kernels when I just showed you that dn's are not good kernels. Well, we're going to come back to this later. We're going to try and modify the dn's a bit to discuss other types of convergence of Fourier series for continuous functions. But right now I want to take some time and just examine this a little bit closer. So I guess my question is, how can we have integral of the dn's over t equals 1, but integral over t of the absolute values of dn x dx tend to infinity. So how do these two things reconcile with each other? What how does this happen? Does anyone take a crack? I'm not asking for something too deep, but how can we have a function which integrates to 1 if I don't put absolute values around it, but when I put absolute values around it, it has divergent integral? What's going on?
Peak oscillation.
I am seeing. I heard a couple different people talking, and some people making the right pictures with their fingers. So somebody try again. I couldn't quite hear.
It's got a lot of negative and positive values.
Yeah, exactly. So we get a convergent integral here because of oscillations, right? And so finiteness of dn of this integral of dn is due to cancellations between the positive and negative values that the function takes due to oscillation. Okay. So the logic, the unfortunate logic of this, or the thing we can deduce, is that the convergence of Fourier series, so the issues about pointwise convergence of Fourier series, is a delicate matter, right? And in order to kind of fully understand the picture, we're going to need to exploit these. We can't do things that as brutal as put absolute values inside integrals. Rather, like we did in the proof of showing that when we have a good family of kernels, that's kind of telling you that absolute values can come right in. We can't put absolute values inside integrals. We're going to need to exploit the oscillations of dn to deduce convergence properties of Fourier series. So logic is convergence of S and F may be very delicate. And might even fail, and as we'll see, may even fail at points of continuity. Okay, so how far can we get? So I'm going to diverge from the book for a bit, and kind of show you how far we can get by just exploiting oscillation. And I'll try and show you how to exploit the oscillation in the DNs. So I'm going to present something that's a little bit that's a little bit technical, and it might be one of the most technical things we'll see in the class. And so just take it with a grain of salt. This is a technical theorem, meaning that it's not obvious, and I need to think about it each time. I think about it really hard each time I give it a try. Okay, so we proved convergence for C2 functions, right? And I want to try and lower that as much as I can. So I want to get C1 functions, and in fact, I claim we can go even lower. So I'm going to make a definition. We'll say that F is a C on T for 0 less than, strictly less than, alpha strictly bigger than 0 and less than or equal to 1. If the following norm, the C alpha norm of F, which is defined to be the supremum over all x and y and t of f of x minus f of y, or maybe I'll write this like this, x minus y divided by y to the alpha. If this supremum is finite. So this is called the C alpha norm of the function. I'm going to introduce one more norm. So what's called the uniform norm for continuous functions. F is in sorry, maybe say the natural norm to put on the space C0t is what's called the sup norm of f, or the L infinity norm of f, which is just designed to be just the supremum of the function of the absolute value of the function. Okay, so I'll use this notation instead of writing sup over all x and t of fx. I'll use this notation for the size of f. This is the size of f, and the C alpha norm. So for these are called so if f is in C alpha, we say f is Helder continuous with exponent alpha, and if f is in if alpha is equal to 1, we say f is a Lipschitz function. Okay, so this is just some terminology. So these the C alphas are called like the Helder classes, and when alpha equals 1, we give that a special name, attribute that space of functions to Lipschitz. And so what are examples of C alpha functions, or C1 or Lipschitz continuous functions? So one, like if you have a corner like this, so it's a weaker notion. So if I put alpha equals 1 in there, that looks a whole lot like the difference quotient you evaluate if I put alpha equals 1 in this quotient here. It looks exactly like the quotient you evaluate when deciding whether a function has a derivative at a point at a point x, for example. But to say it's differentiable, I would need the limit as y tends to 0 of this quantity to exist, right? Here, I'm not asking for the limit to exist. I'm just asking for this quotient to be bounded, right? So in particular, this allows for when I have C1 or when I have a Lipschitz function, it allows for functions with corners like this. So a function with a corner like this is a Lipschitz continuous function, because right, the difference quotients to the say these two lines have slope 1. To the left here, I'm seeing limit 1. This limit is bounded by 1 from the left, and it looks like -1, so an absolute value is bounded by 1 from the right as well. But right, this function is not differentiable at the point where the corner is. And when alpha is less than 1, that allows like some worse type behavior. So functions with cusps, and the angle allowed in the cusp is related to this exponent alpha. All right. So what I'm doing is I'm like saying like, okay, I want to have some, when I look at this space of C alpha functions, I want something I want to allow for more than just differentiable functions, functions that are better than just a continuous function, because I have some control over how they fail to be differentiable at points where they're, so they're continuous functions, but they might fail to be differentiable, and then this alpha index here is telling me how badly the corners and the cusps might be. I want to erase this circle. Does this definition make sense? Okay, and you should think of like it was alpha, like alpha going to 0 is more like these cusps becoming worse. So sort of it's farther and farther away from a differentiable function, and when alpha is equal to 1, these are kind of just very close to differentiable functions, or you just might have some corner.
Question?
Go ahead, Michael.
We might have the same question. Do you know what happens? Does something happen at alpha equals 0? Do we recover just continuity, or do we get something weaker than that?
You mean if I like consider this like the whole family and like take alpha, let alpha go to zero?
Yeah.
Uh, um, th- that that's that's kind of delicate. I think you should think of it more as like fixing an alpha at the outset, and then considering a class with those alphas. But I think when in um, yeah, I mean, so the point that the notation is suggestive, right? That when I'm putting C0 for continuous functions, and that's what you should think is letting alpha go to zero. I'm recovering sort of the continuous functions that way. But I don't think you should think of any limit of alpha tending to zero. I'm not sure if that makes much, with that making a lot of sense. Does that make
Sure.
sense?
I guess my new question would just be, if you take alpha equals 0 in this definition, do you get the definition?
If I get if I take alpha equals zero in the definition, then what? Then I have one in the denominator, right? And then so that just gets rid of this term in the denominator, and then I just have this, right? I just have the difference, the soup of differences between f at different points, right? And that recovers exactly this norm, because it's comparable, right? So if I use this norm for continuous functions, I would get twice the maximum, right? This is bounded above by twice the maximum, twice the maximum the function takes, or twice the soup. So we would say that those two norms are comparable, and I could have written down here f of x minus soup over x and y of f of x minus f of y, but that would just give me twice. If I measured functions in that way, I would just get twice the size, as opposed to like just using this norm. So yeah, you're right. That like the reason why I made this one look a little simpler is because there's kind of no real added benefit of taking this difference. Whereas here, if alpha is bigger than zero, this is really telling us something about how the function looks near how it tells you something, something like about this behavior. Does that make sense? Okay. All right. So what's so the theorem that we're going to prove, or we're going to prove a couple theorems. If f is in C alpha of t, for any alpha bigger than zero, then S and f minus f. So if I look at the supremum norm, so the supremum norm is a good way to measure uniform convergence. It's equivalent to measuring uniform convergence, or this is often called the uniform norm, because for this very fact. Then this tends to zero as n tends to infinity. So I have uniform convergence, i.e., I have of the Fourier series in C alpha, as long as I take alpha to be bigger than zero. So this is awfully close to the result that Fourier imagined. I can't quite. It's not quite saying. I'm not quite saying something about continuous functions. We'll see later that'll end up being false. But if I assume any additional regularity for the function, if I assume any additional control of how smooth the function is, then I get uniform convergence of Fourier series. So this is a really powerful theorem. Right? It's actually the proof is elementary, in that it's essentially gonna be a calculus proof, but it's delicate. So meaning it involves some refined analysis. It's tricky. So I think this is a hard theorem, but we can do the proof. It's just going to take a little bit of time. Okay, So what else did I want to say? Okay, let's just stick to here. I'm gonna stick with here. So the idea is that we're gonna try to the idea we have from just looking at the Dirichlet kernel is we're gonna try and see if we can exploit the oscillations in the Dirichlet kernel. So proof is idea. Exploit in Dn. Okay, so let's take a point x and then consider the difference S in x minus f of x, just like before. And I'm going to use the fact that the Dirichlet kernel integrates to 1 by doing the same trick I had before. So this is equal to 1 over 2 pi, integral from minus pi to pi of f of x minus y. On the one hand, I write the first term as convolution with the Dirichlet kernel. The next term, I'm going to use the fact that the Dirichlet kernel integrates to 1. This is minus f of x dn y dy. And this is here I've used using and then I'm going to split this into 2 regions, just as before. So even though I don't have this this notion of good kernel, I'm still going to argue a little bit like this. So this is equal to the integral over y less than delta of this quantity, same quantity inside, plus the integral for y bigger than delta, y between delta and pi, absolute y between pi. And I'll call this 1 plus 2. Okay, so and I'm not going to specify delta yet. In fact, I'm going to only tell you what delta. We're only going to choose delta at the very, very end of the proof. For some delta in between, say 0 and pi, to be determined, so TBD. We're going to pick delta at the end. And now let's estimate each piece, and we'll do each piece differently. So 1, for 1, maybe let me say this differently. For 1, we're going to use the bound that's in your homework that the Dirichlet kernel is less than or equal to constant times the minimum between n and 1 over y. And okay, so let's take care of 1. So 1 in absolute value is less than or equal to the I'm going to just throw absolute values inside. Y strictly less than delta. And I have here f of x minus f of x minus y. And this is less than integral over delta. Maybe let me cheat a bit with this this iPad. I'm going to write this suggestively. So so what do I know about f? I know that it's C alpha continuous. So I know I can divide here by y to the alpha and multiply by y to the alpha, and I'll be okay. I'll be able to control the size of this, right? And then it costs me a y to the alpha up here. But remember, y is very small, so y to the alpha, where alpha is a positive number, is very small. So this is helpful. So being able to divide by y to the alpha and multiply by y to the alpha is helpful to my cause, right? Because now I have a mechanism for making this small. And what am I? How am I going to make it small? Well, I'm going to make delta very small, right? So, and then now I can brutally estimate this dn of y. So this is less than or equal to, well, I can pull out the C alpha norm of f. That's appeared. I can bound this by its soup, bound this first factor by its soup, and then I'm going to use this bound for dn. Y to the alpha times the minimum of, in fact, I'm good actually. I'm gonna bound this. I'm not gonna worry about this this n, since I already have this little factor y to the alpha here. I can use the bound that dn of y is less than or equal to 1 over y. So here I have alpha minus 1 dy, which is less than or equal to f times c alpha times, what do I get? Well, since alpha is bigger than 0, this integral converges, right? And I just get, after integration, I'll just get delta to the alpha. Right, so I get something finite, I get something, I know it's finite times delta to the alpha, where alpha is a positive number. So if delta is small, then this thing is, I can make this thing small. All right, that's good. And later in the proof, I'm going to choose delta depending on n. So I'm going to make delta to be a function of n. So I'm going to try and make 0. But I have to do this carefully because I still haven't told you about the other piece, which is a little bit scarier. And I also haven't used any oscillations yet, right? What I used was f is in C alpha, but I haven't used anything about oscillations. So I know that's going to come in. So the delicate part of this argument is coming in estimating 2. So for 2, use oscillation.
Quick question.
Yes.
When we divide and multiply by absolute y to the alpha, is there an issue where we introduce something at 0 that looks bad?
No, right? Because we're just multiplying by 1, right? At 0, so let's multiply by the function y to the alpha divided by when y is not 0, and multiply by just 1 when y is equal to 0. So that's just shorthand for doing that, right? You're right. Like I shouldn't be dividing by 0, right? But let's just say I'm multiplying by 1 when y equals 0.
So we sort of define 0 to the alpha equals 1, and that's continuous and things. It's okay.
No. Okay. So okay. So we need to be yeah. So let me go back up a second. So this doesn't quite make sense, right? When y equals 0, right? And what I should say here is this is, and then if f is but again, this is only interesting when y tends to 0, right? This thing being finite. If y were bounded away from 0, then this thing would be bounded just by using the continuity of f, right? So what I really mean in here is I should really say y not equal to 0 here as well, right? So this is a supremum over x and y and t, where y is not equal to 0 to make this make sense, right? And so that's what I mean here as well. Is that okay?
Okay.
So
yeah.
I'm really not. I promise what I could do. This is kind of tongue-in-cheek the way I've written this. If you think for a minute, you can do this. You could do this carefully using the fact that the C alpha norm is finite.
Okay.
So right, alternatively, like you could bound this quotient. This quotient by you could write that. Another way of writing this would be to bound this quotient by C. I've written it like this because it looks like the the limit you take when you take a derivative. But I could put y to the alpha over here, right? I could say that these differences are bounded by constant times y to the alpha, and that way you can allow y equals 0 in here.
Okay, yeah, that looks good.
Thanks for keeping me honest. Okay. Okay, so that's the first piece where I used my little additional regularity or smoothness for y was enough to make sure that this integral converged. For 2, let's use oscillations. So this is tricky because I can't. One way of using oscillations is integrating by parts, but I don't know enough about f to do that. Right? I'm not assuming f is differentiable, so I can't quite integrate by parts. So I'm going to try and do the next best thing. So this is the integral over y bigger than delta less than pi of f of x minus y minus f of x times dn of y dy, and I'm going to try and write this. I'm going to try and write this differently. So first, I'm going to remember my formula for the Dirichlet kernel. Remember, it's sine n plus 1/2 times y divided by sine of y over 2. But I'm going to put that sine of y over 2 over here. dy. So this is just equality. And I'm going to call this function here to save myself space. I'm going to call this h y, hx of y, I'm going to call it. So maybe let me write this. I'm worried about this getting cut off. So this, or rather, sorry, is the function h sub x of y. It's a function of y by x which we've fixed. Okay, so this is and then I'm going to use a following fact. So this is how I'm going to exploit oscillations. I'm going to write sine of n plus 1/2 times y as I'm going to use the fact that sine of theta plus pi is equal to I'm going to write this. Sorry. Sine of theta is equal to minus sine of theta plus pi. If I shift sine by pi, the sine function by pi, I get it oscillates, so it turns into minus sine. So I'm going to do that here. This is equal to minus the integral from delta between y between delta and pi of hx of y times sine of n plus 1/2 times y plus pi over n plus 1/2 dy. So this is going to be my version of non-integrate by parts. I'm going to use this is the key observation, really, that the rest is going to be brute force, but this was the key observation, that sine oscillates. All right, so and then the Dirichlet kernel is made up of sines, and so I'm going to exploit those oscillations. And as n gets really big, this is oscillating faster and faster, right? Okay. So this, and now my next clever step is I'm going to change variables. So this is equal to oh no, I'm not going to change variables yet. Or yes, I am going to change variables. Okay, I'm going to try and write this in one fell swoop. sorry, so 2 times 2 times 2 is equal, I'm going to write this integral Roman 2 in 2 different ways. So I'm going to add those together. So twice 2 is equal to the first representation, where I just have the integral of hxy against dn of y, the hxy against sine of n plus 1/2 y. And then I have this other representation of it. And I'm just going to add those 2 together. So this is equal to integral over y bigger than delta. Let me just forget about pi for a second, just to shorten my notation. Hx of y sine n plus 1/2 y dy, and then minus, and I am going to change variables in this integral here. So I'm going to replace, I'm going to shift by my new variable is going to be y plus pi over n plus 1/2. All right, so what I get is the integral minus, and I need absolute y, change of variables, minus pi over n plus 1/2 is bigger than delta of hx of y minus pi over n plus 1/2 times sine of n plus 1/2 y dy. So I wanted to make these two match up with each other, because now I'm going to try and combine these two integrals. Okay. The problem, I can't just combine them right away because my regions of integration don't match up, right? But let's, so what are my regions of integration? This is, so on the one hand, I'm looking, here's 0, here's delta. The first integral, I'm integrating up here, and the second, and here, right? In this first integral, the top integral on the top of the page. And then the integral on the bottom of the page, I'm integrating to the right of delta plus pi over n plus 1/2, and then to the left of minus delta plus pi over n plus 1/2. So I'm integrating in this region. So in some places these overlap, right? And when they overlap, I'm going to combine them, and then I'm just going to add the rest of the junk that I had. And note that the junk that I'm missing is are very small intervals, right? I'm just missing this interval here. I'm going to overcount one. I'm overcounting this integral, and this one I'm missing in the top line. But these two little pieces are very small, right? They're of length roughly 1 over n, which is good because 1 over n is something I'm going to make go to infinity. So altogether, what do I get? This is equal to the integral of 3 pieces, integral of y bigger than delta of hx of y minus h sub x of y minus pi over half of times sine n plus 1/2 y dy. And then by doing that, I've overcounted I've overcounted this region here. So I'm gonna subtract it off the part I overcounted, which means I'm gonna add back on this integral over that region, So plus integral of between delta and delta plus pi over n plus 1/2 of hx and this I missed this region here for the second interval. So I have minus integral from minus delta to minus delta plus pi over n plus 1/2. Sine n plus 1/2 y dy. Okay, and you see okay, so now I'm going to estimate each of these pieces separately. These three last pieces. So let me re-up the Dropbox too. So this is I have to estimate each of these pieces, and I'm going to make a claim. And I'm going to give you this claim for homework next week. So I'm going to make a technical lemma here. One is that hx of y which is equal to the absolute value this is less than or equal to a constant times the L infinity norm of the sup norm, the uniform norm of f, divided by delta, if y is bigger than delta. So in this first piece, I have a problem. I have a problem in the denominator as y goes to 0, right? Because sine goes to 0. But if I'm bigger than delta, then I'm okay, right? Right. So that's roughly the proof of this, but I want you to do this carefully. And then claim 2. So I'm going to use this estimate. Maybe I'll call this 1 and 2. Estimate 2 is I'm going to estimate the difference of this type of difference. So hx of y minus h of x of y plus tau, where tau is going to be a small number, is less than or equal to a constant, some constant times tau to the alpha times the C alpha norm of f divided by delta plus the infinity norm of f times tau divided by delta squared. So these are two very technical estimates that I'm not gonna do in class because they're going to be even harder to watch than the rest of the proof. But I'm going to ask you to do these in the homework. Again, it's basically follow from just the definitions of C alpha of the C alpha space. And let me give you some hypothesis here. If y is bigger than delta, which is bigger than 2 times tau. Okay, so this holds for all y tau satisfying these properties.
Professor, is there an absolute value on the tau, on the final tau, or is there not?
Sure. Sure. Yeah.
Okay.
But we're going to think of tau here as a positive number. Our tau is going to be pi over n plus 1, n plus 1/2.
Yeah.
Okay. So okay. So what this means is that well, I'm just going to brutally use these two estimates in these 3 lines. Okay. So I claimed using 1 and 2. So using 1 and 2. 2 in absolute value is less than or equal to into the minus alpha times the C alpha norm of f divided by delta plus into the minus 1 times the L infinity norm of f divided by delta squared. And here, I mean, this is the twiddle notation, less than or equal to with a twiddle in the bottom notation that I was talking about. So less than or equal to 2 is less than or equal to a constant times this quantity. All right, so sorry, and I should say one more thing. So this is true as long as delta is bigger than 4 over n. So this is true only for large enough n. And again, the way we go about it is use tau is equal to pi over n plus a half. And as long as delta is like this, then 2 tau, 2 times pi divided by n plus a half, maybe 4 bigger, 8. Like something like this. Okay, so as long as I choose n sufficiently large. So I haven't told you what delta is, but whenever I fix delta, I'm going to choose n large enough so that this is true. Okay, and then I claim this estimate. And I promise that if you go back in your notes and look at what I've written down, I think I've been careful enough that you can easily see this estimate for Roman 2, given these 2 technical estimates above and the size of h. Okay. Okay, so now we're going to optimize. So we have 1 plus 2. We need to estimate 1 plus 2. And recalling our estimate for 1, this is less than or equal to. So let me rewrite this whole thing. So Sn f of x minus f of x is less than or equal to 1 plus absolute 2, which is less than or equal to, for estimate 1, we had the C alpha norm of f times delta to the alpha. And then for 2, we obtained n to the minus alpha times the C alpha norm of f divided by delta plus n to the minus 1 times the L infinity norm of f divided by delta squared. And as long as delta is bigger than 8 over n. All right, now what we're going to do is optimize our choice of, there's some competing factors here, right? So here, in these last 2 terms, delta being small is bad, right? Delta is in the denominator, and in this term, delta being small is good. But note that in these last 2 terms, we have, even though we have deltas in the denominator, we have n's in the numerator. So we're going to optimize we're going to choose delta to be a function of n, right? So we're going to try and choose delta to be a function of n, so that I get small in all of these. I get three terms which go to 0 as n goes to infinity. So now we optimize. So optimize in delta. So we take, I'll save the suspense and just take delta is equal to n to the minus alpha over 3. Should work. And then since alpha is less than 1, alpha over 3 is less than 1, and so we have no problem with this property, right? Delta is bigger than 1 over n for n large, and so with this choice, this is less than or equal to C alpha norm of f times n to the minus alpha squared over 3 plus n to the minus 2 alpha over 3 times the alpha, and then I have plus n to the minus 1 plus 2 alpha over 3 times f infinity. And so this goes to 0 as n goes to infinity, as long as is bounded, which is true, right? Which we have as long by assuming that f is in C alpha. So C alpha functions are necessarily continuous, so they have bounded sup norm, bounded uniform norm. So both of these norms of f are finite. So here we just have number times this factor going to 0, number times this factor going to 0, and then number times this factor going to 0, fixed number times this factor going to 0. Okay, so that completes the that completes. Are there questions about any of it? I'm kind of assuming that was too fast for everybody, and maybe even including me. But I did it already earlier today in my notes, so I think this is all correct. So if it would just seem too fast, please try to go over it again slowly. Try to reproduce it for yourselves. This is not in your book, so it's I would take this as more as being out of intellectual curiosity rather than something that's going to be on the final. This is a really tricky argument. And more like just like tricky, not like I used any deep results. What I did, the deep thing that I did use, just I tried to exploit oscillation of the Dirichlet kernels. So I just want to show you the power of that, because later we're gonna keep working, of course, with these convergence properties, but using the kind of the we can, by exploiting oscillation, we can do a lot better than we can by just brutally putting absolute values and trying to look for absolute convergence. So
I've got a quick question for you about this proof.
Yeah.
So I guess just going back to like the way beginning. I'm just recap in my head what exactly we showed here. We showed that.
Yeah.
Right, of the Fourier.
So we showed that sorry, I can't get my phone to hang up on the computer. There it's on my iPad. Sorry, my car is getting fixed. That's what that was. The car is finished. Okay, so what exactly did we show? We showed that if we looked at the partial sums we took a function that's in C alpha and then computed the partial sums, the partial Fourier sums, then those partial Fourier sums converge uniformly to f as n goes to infinity. And how did we do it? We just compared the difference of these two objects, and then tried to show that this, if we put absolute values around this difference, then it goes to 0 as n goes to infinity, independently of which x we picked. So we're trying to prove uniform convergence. So in the end, all we did was we expressed this as we used the fact that Sn of x is given by convolution with the Dirichlet kernel, and then expressed this integral as two pieces, and we showed that each piece can be made small by choosing n large. Is that roughly?
Yeah. No, I got it. Cool.
Yeah. So at the end,
a lot that happened. I want to make sure I really understood exactly what we did again. So
yeah, this is a highly technical argument. And the kind of the main point was just there's two things to keep in mind. One was that the Dirichlet kernel is not that great near 0. It looks like 1 over x. But if we assume a little bit more, and for piece 1, if we assume a little bit more about f, namely that it's C alpha, then we can get this little piece of y to the alpha here, which now gives us a convergent integral. If I didn't have y to the alpha here, I would just get y to the -1 there. which diverges, right? So the extra regularity of F helped us get something small near the origin. And then away from the origin, we noted that the Dirichlet kernel there's a sine function appears in the numerator, which makes this thing oscillate like crazy. And we exploited that in estimating part 2 in kind of a roundabout way, like without integrating by parts. We used the fact that sine oscillates. So this is the key step in 2 was really this observation, and then a lot of like technical stuff to make this useful, I'd say.
Thank you.
Okay, guys. So I'll stop now, and then if there are additional questions, we can move over to my office hours. And then in office hours, there are going to be 2 presentations. Tyler's going to present the first problem in the homework, and Samuel's going to present, I think, homework problem number 5, if I'm right about the numbering of the homework problems. Okay, so see you in office hours, who'd ever like to join me, aside from Tyler and Samuel, who I'm guessing are going to be there. All right, see you guys.
Thanks.